This presentation is performed by Group 27. In this video, we will be exploring the idea of why golf balls have dimples on their surface. Most would consider that a smooth sphere would be sufficient to act as a standard playing object in the game of golf. However, clearly this is not the case, as in today's game, the most commonly used golf balls are dimpled in some way. Almost all of the major golf ball suppliers manufacture golf balls with circular dimples. So, what is the reason for this decision? When a golfer goes to strike a golf ball, there are only two controlling factors that affect how far the golf ball can travel. That is, the force at which the golfer hits the ball and the properties of the golf ball itself. Since there is a limit to how hard a ball can be hit, a lot of time and money has been invested into optimizing the design of the golf ball with respect to its aerodynamics. From this, we can hypothesize that the dimples were designed to increase the distance a golf ball can travel, and that it is possible for deviations from the standard circular dimple design to be created. Before investigating, it should be understood that there are many factors contributing to the aerodynamics of a golf ball, and correspondingly, there are many factors that can be affected by the addition of dimples on the golf ball. Our group specifically chose to look at how dimples affect the drag force that a ball experiences while it's still in the air. From this, we hope to gain a better understanding in the field of aerodynamics and apply that knowledge to other related engineering topics.
To provide some background information, we will talk about the physical phenomena that act on a golf ball while it is in the air. First, the drag of an object is a force that acts directly opposite of the direction of motion. There are two types of drag that contribute to the total drag force: frictional drag and pressure drag. Frictional drag occurs from the friction between a fluid and the surface of an object, such as air hitting the front of a ball in our problem. As seen in the figure on the right, there's friction that occurs on the surface of the body. When the surface is smooth, there is less contact area between the object and the medium, while the opposite is true for a rough surface. Meanwhile, pressure drag is due to the eddying motions, or swirling gusts of wind, created from an object passing through a fluid. In other words, it's when an object forces a separation of airflow. In this visual, you can see the difference in pressures of an object depending on its shape. The less flow separation that occurs on the shape of an object, the lower the drag differential is between the front and back of the body. Essentially, the lower the pressure differential correlates to a lower drag force. As we can see, the least amount of separation occurs on the airfoil. However, it's not feasible to change the shape of a golf ball for this reason. So what can we do to help reduce pressure drag? This is where the concept of dimples come into play. When dimples are added to a golf ball, frictional drag is increased while pressure drag is decreased. However, in terms of impact, the effect of pressure drag on a golf ball's movement is much greater, so we will ignore how frictional drag affects the golf ball. The main factor affecting pressure drag is airflow. We will look at how dimples are designed to optimize the airflow around a golf ball. To delve deeper into this topic of airflow, we can divide this subject into two categories as well: laminar flow and turbulent flow. Laminar flow is when the air travels smoothly along a surface in a regular path. It is widely known that airfoils are designed to take advantage of this phenomena. However, the case is different for spherical objects. In laminar flow, the air is separated quickly on contact and hugs the object as it moves. This quick separation of air creates a large wake region following the object. The wake region consists of swirling air, known as eddies, which try to pull the ball backwards, resulting in heavy drag. Turbulent flow is the polar opposite of laminar flow. The airflow around the ball travels in an irregular and sporadic pattern. What happens when dimples are added to a spherical object is that airflow changes from laminar to turbulent. This turbulence sucks the air into the ball as it pushes past, allowing separation to be delayed. This results in an overall smaller wake region, as a smaller vortex of eddies are created to oppose the movement of the ball, leading to less drag.
So rather than directly looking at the drag force, we decided that it'd probably be a better idea to measure the pressure difference between the front and the back of the golf ball instead. This is mainly done because the pressure measurements are directly available in ANSYS, whereas we would be required to calculate the drag forces. So now, let's take a look at why measuring the pressure actually works. Here we have Bernoulli's principle. This equation is based off of the idea of the conservation of energy. It basically states that the rise in pressure in a flowing liquid is accompanied by a decrease in the velocity of that liquid. The inverse is also true. If a liquid's pressure decreases, then its velocity will increase. Now, looking at the general equation for pressure, where pressure is equal to force over area, we can rearrange this equation to get force equal to pressure times area. By isolating Bernoulli's equation for the net pressure, we can now sub in the result into the general pressure equation. This results in the drag force equation, where ρ is mass density of the fluid, c is the drag coefficient, A is the reference area, and V is the flow velocity relative to the object. The key thing to take away from all this is that the drag force, Fd, is proportional to pressure. For this project, we decided to use 3 different golf ball designs. The first being a smooth golf ball, the second a golf ball with circular dimples, and the third a golf ball with square dimples. The first 2 golf ball designs were chosen based off the fact that we wanted to investigate why players in golf use dimpled golf balls over smooth ones. The third design was chosen to explore the idea of implementing different dimple designs and how these would in turn affect the overall aerodynamics of a golf ball. To get the answers that we needed, a model was set up in ANSYS Fluent. In this model, we had one of our golf ball designs enclosed in a cube. This cube was made up of 3 main components: the inlet, the outlet, and the 4 surrounding walls. In our model, air will be shot at from the inlet, where it will flow into the area contained by the 4 walls and over the golf ball. It will then escape through the outlet. The absolute pressure was measured at a point on the front of the golf ball, facing the inlet, and at a point on the back of the golf ball, facing the outlet. The simulation was run for exactly 100 iterations per golf ball, and the measurements of pressure at that final iteration were used in our analysis. Now, there were 2 assumptions made when we created the model for our simulation and when we actually ran our simulation. These assumptions were mainly created with the purpose of simplifying the problem, as it would have been too complex given the time constraint. Firstly, there is no rotational movement to the ball. And secondly, the ball won't actually be traveling in the model. Rather, we will be shooting air at the golf ball from the inlet to simulate the ball's movement. The speed of the air will be based on the average amateur male golfer's club speed of 93.4 miles per hour, which equates to about 41.6 meters per second. So just to reiterate, what we initially sought out to investigate was how exactly dimples were affecting the flight of the golf ball. We got a good idea conceptually of what the answer could be from the background section, but now, using our simulations, we will actually be confirming these concepts. In the end, was our investigation successful? We managed to create simulations for all 3 golf ball designs, with the smooth design and the circular dimple design being shown here. In these videos, we have the simulation being viewed from the XY plane and also from an isometric point of view. Using the simulations for these 2 designs, we were able to get a clear indication as to what was happening in terms of the turbulence experienced by the golf ball, the resulting wake region, and also the overall pressure distribution along the golf ball. So for turbulence, let's look at the smooth golf ball first. We can see that the path that air travels on relative to the surface of the golf ball, which is indicated by the black curve, is constant and smooth. In other words, it is laminar. This is in contrast with what can be seen with the circular dimpled golf ball. With the addition of dimples, all of a sudden, ripples start to form in the boundary layer between the air and the golf ball's surface. This effect is what we previously described as turbulence and is what keeps the boundary layer of air attached to the golf ball for a longer duration of time. Based on our results from turbulence, when we look at the wake region of the smooth and circular dimpled golf balls, we should be seeing results similar to what was described in the background section. That is, by having a layer of turbulence on the golf ball's surface, the separation point for the air should be delayed, resulting in a smaller wake region. The snapshots taken during the simulation prove that the expected result is indeed true. The smooth golf ball on the left ends up having a comparatively larger wake region than the dimpled golf ball on the right. And finally, let's now see how the pressure distribution along the golf ball behaves. For these plots, the majority of the points are represented by the color green, while the red and white points represent the location of where we're measuring the front and back pressures at. For the smooth golf ball, the red dot's value is noticeably larger than the white dot's value. This can be interpreted as having a higher pressure differential. The numerical value associated with this difference is 3.25 times 10 to the 3 pascals. As for the dimpled golf ball, the magnitude of the 2 pressures are relatively the same, meaning that there is a small pressure differential and correspondingly a small pressure drag acting on the ball. This value comes out to be 1.2 times 10 to the 2 pascals. By comparing the pressure differences between the front and back points of the 2 graphs, we can conclude that the overall pressure drag acting on the circular dimpled golf ball is much lower than that of the smooth golf ball. In fact, it is lower by a magnitude of 10.
So now that we have finished comparing smooth and circular dimpled golf balls, let's look at what happens when we change the shape of the dimples, more specifically a square dimple. We will be taking a look at the square dimpled golf ball simulations. So how does this design differ from the smooth and circular dimpled golf balls? Turbulence. In the process of air moving around the square dimpled golf ball, tiny pockets of turbulence or air disturbance is created on the surface. However, the overall shape of the airflow around the golf ball remains extremely similar to that of the smooth golf ball, rather than the circular dimpled golf ball. Wake region. For this particular design, the wake region shows no significant decrease in size, but rather it shows to increase instead. Pressure distribution. The shape of the scatter plot is similar to the smooth golf ball. However, the maximum pressure located at the red dot is significantly higher, with the pressure at the front of the golf ball staying almost exactly the same. The difference in pressure for the square dimpled golf ball is much greater than the other two designs. Pressure table. From this table, we can see that the square dimples act to increase the drag force rather than decrease it. The factors covered previously also contribute to this conclusion, along with the fact that the pressure difference in the square design is significantly larger than both the other golf balls. Why is this the case? The larger pressure difference and turbulence was not expected with square dimples. It is possible that our understanding of these results are getting abstracted due to the fact that we are not taking into account other factors in aerodynamics, such as Reynolds number, Magnus effect, and the assumptions we made when we modeled the simulation. The geometric shape of the square dimple doesn't allow for a tight flow of air. Again, this is just speculation. We won't have conclusive reason for this result until we conduct further investigation. Verifications. Based on the research done by the Mechanical and Manufacturing Engineering Department at RMIT University in Melbourne, dimples affect the aerodynamics of the golf ball. In circular-shaped dimple golf balls, drag coefficient is shown to decrease. As shown in the graph, 11 golf balls with different roughness were compared with the smooth golf ball, and it was found that golf ball with the roughness had a lower drag coefficient than the golf ball with smooth edges. Through this research paper, the results indicated that the increase of the dimple depth ratio or surface roughness of the golf ball can shift the transition to a lower Reynolds number and increase the drag coefficient. The result also established a positive linear correlation between relative roughness and drag coefficient. Furthermore, different dimple designs, shapes, depth, size all affect the drag force experienced by a golf ball by varying amounts. Research also shows how dimple shapes also directly affect the wake region, separation point, and drag force, all by measuring the drag coefficient. The drag coefficient of an object becomes larger when they have dimples in the shape of cones, arcs, or trapezoids. The analysis of golf balls contains several different factors that were not accounted for but shows different graphs that use Reynolds numbers, Magnus force, and spin. A logical follow-up on this investigation would include measuring such parameters and testing how it affects with other forces that act on the golf ball.
The results from the study can be applied to the field of aerodynamics as a whole. The use of dimples to reduce the amount of drag acting on an object is useful for optimizations. The concept can be applied to new and existing solutions to make them more efficient. For example, cars or planes, which heavily rely on it being aerodynamic, can be improved upon by dimpling the mechanical frames. An optimization such as this can greatly increase their fuel efficiency. The data gathered can be used as a starting point for further analysis. We studied the effect of one specific component in golf ball design, so there must be a handful of other factors that come into play that were not considered, such as dimple spacing, size, and depth. New studies can be performed to discover the best combination of properties that can create the most aerodynamic golf ball possible, which can be used in a professional setting. What we initially set out to investigate was concluded to be false. Dimpled golf balls are not necessarily superior to smooth golf balls in terms of experiencing less drag force. From the graph of our final results, it can be seen that square dimples cause the largest pressure differential, followed by a ball with a smooth surface, and that circular dimples generate the least drag force by a substantial amount. It is plausible that dimples affect the aerodynamics of a golf ball positively. However, that is not correct for all cases. As for further investigation, the accuracy of the solution can be improved by adding complexities to the analysis. Our group did not account for other environmental effects such as the ball spinning, the Magnus effect, and Reynolds number. In this video, you can physically see how a ball curves in the air due to these effects.